This week, we was wondering how an electric shaver works. Then we visited a folding carton manufacturer. But first, here's the lowdown on why computers use ones and zeros. Even I could count higher than that. 2, 3, 4, 7, 8, 10, 12. What?
I'll bet there isn't a single person watching right now that hasn't heard that computers deal with ones and zeros. Yet, it's not often stated why. Fact is, if they dealt with anything else, at best they'd be inaccurate, and at worst, they wouldn't work at all. This tape recorder is an analog machine. It records signals that have nuances. In this case, it recorded the intricate wiggles that my vocal cords produced. This has been a recording. Does a pretty good job of it, too. Now, I took that recording and copied it, and then I copied the copy, and so on. Here's that same recording after 4 trips through the process. Now it contains a buildup of noise and static and hum and distortion. Even in the simplest home computer, the signals will have to travel through hundreds of circuits, possibly thousands. As well as the forms of distortion and interference that plague sound equipment, the computer produces plenty of its own interference. Nothing up my sleeve. Let's make it work. Now, a computer contains thousands of tiny circuits, all operating close to each other, so it can be taken for granted that they'll be interfering with each other. To beat the distortion and interference, the digital computer uses signals that only have 2 possible states. They're either there or they're not there, the famous ones and zeros, or on and off pulses. An electronic system that only has 2 conditions, on and off, can be made immune to interference by regenerating the signal each time it passes through a section of circuitry. So even if the input has a little interference, the output will be clean. I've made a little computer circuit here. It simply turns on and off. I also have a control that will add some junk to the signal. Now, the bottom trace on the oscilloscope shows the output of my simple circuit. As I add unwanted stuff to the input, that's the top trace, the output stays clean, because the circuit really only needs to tell whether we mean on or off. In effect, it gets regenerated to its nice, full, clean levels. This is one reason why computers never make little mistakes on their own, only great big, huge, disastrous ones. Because when the static and noise finally gets bad enough, the next circuit in the chain will generate beautiful-looking, regenerated garbage. Now, this system of on and off is great for keeping the signals accurate, but there's a tiny little hitch. You can only count up to 2. It sounds like a major stumbling block, but the counting system we use can only count up to 10. Base 10 uses 10 digits. That's 0 through 9. And when we want to count higher in base 10, we use a second group of digits, and we carry. We know that this number is 10 because our notation system says this location is worth 10. This number is 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 1, 2, 3, 4. 1,234. With 1 base 10 digit, you can count up to 9. That's 10 numbers if you include the 0. Notice that every column you add in base 10 multiplies how high you can count by 10. Base 2, the binary system, can count up to 1 with 1 digit. That's 2 numbers if you include the 0. If you add another column, the count doubles to 4, like this. 0, 1, 2, 3. That's 4 numbers. Another column will double the possibilities to 8, and so on. Now, instead of ones, tens, hundreds, and thousands, there are 1s, 2s, 4s, 8s, 16s, and so on. To figure out a base 2 binary number, you follow the same procedure as you do in base 10. Add up the places. So this number would be 1 times 8 plus 0 times 4 plus 1 times 2 plus 1, 11. And now on the Acme School of Stuff, we will watch this sophisticated piece of modern technology count up to 255. These light bulbs represent the digits 0 and 1. When they're not lit, we're going to call them 0. When they are lit, we'll call them 1. The numbers on them are their values. Here we go. Right now we're at 0. No bulbs are lit. And the 1 bulb comes on. To increase the count, we're going to have to carry. The 1 bulb goes out, and the 2 bulb comes on. Now the 1 bulb comes back on. This is the binary number 3. 1 times 2 plus 1. Still counting, the 1 bulb's going to go off. That'll carry to the 2 bulb, which is on. That carry will take the 2 bulb off, but carry it to the 4 bulb. Okay, that's the number 4. Now to step to 5, the 1 bulb comes back on. None of the digits have to carry. So we have 1 times 4 plus 1, 5. Okay, don't panic. I'm not going to describe the sequence all the way up to 255. This is a repetitive sequence, and there's a simple way to look at it. As a computer counts upwards, each time a lower value bulb turns off, the next higher value bulb changes state. If it's on, it goes off, and vice versa. If we were to stop the count, freeze it at any place, all we have to do is add up the numbers on the bulbs to get the base 10 number. Each digit in the binary system is called a bit. That's a contraction of the words binary digit. Now, a bit is pretty useless on its own, so computers deal with groups of them called bytes. This 8-bit byte can represent the numbers up to 255. That's 256 numbers if you include the 0. And it's strange but true. The whole first generation of home computers didn't know anything above the number 255. They had to deal with everything in 8-bit bytes. Binary system seems real cumbersome to us because of the large number of bits required to represent large numbers. But remember, every time you add one more bit to the number, the possibilities double. There's an interesting bit of confusion because of this. 1K in base 10 is the mathematical abbreviation for 1,000. 1K in base 2 is about 1,000. It's actually 1,024, and that's how high you can count with 10 bits in a number. Adding one more bit gives 2,048, but we call it 2K. A so-called 64K computer actually has 65,536 memory cells, a tiny little discrepancy of 1,536, and we think they're so accurate. Adding and subtracting is fascinating in base 2. Mathematical operations using only 2 digits leads to strange statements like 1 and 1 is 1, and 1 or 0 is 1. Multiplying and dividing are also done with repetitive adding and subtracting. Everything a computer does is tedious, particularly any math problem with a result greater than 255. There's one little trick they have up their sleeves that makes them look so clever. They're very, very fast.
Potato sticks.
What do you think is the most common sight in your supermarket? Dairy goods? Cereals? Household products? Baked goods? Wrong. It's cartons. Those thousands of cartons come from a folding carton manufacturer. This building houses quite a bit of interesting machinery. Cartons start out in big rolls. This paperboard is made from up to 90% recycled material, and any waste from this plant will be sent back to be re-recycled. Printing is the first step. Most color printing uses only 4 colors, 3 primaries and black. Carton printing often uses more colors. This offset press can do 6 colors, 2 different inks at each of 3 sets of rollers. The extra stages are necessary because of the unique, bright colors that packaging requires, and the inks are custom mixed for each different package. In offset printing, the image from the printing plate is transferred first to an intermediate roller, then to the paperboard. Here they're checking to see that all the colors are printed in the right spots and there are no streaks or other imperfections. This is the German version of Bounce fabric softener. The English version of Bounce is about to be pressed into this. It's a die that will cut and crease the box. The exposed metal ridges will add the creases, and knife edges, hidden here by rubber strips, will trim the box to shape. Waste comes out the bottom and is sucked away to be recycled. Sample boxes are folded by hand and glued to make sure that the perforations will break with the right amount of force when you get them home from the store. Other die-cut and creased cartons come here. This operation is kind of self-evident, but fun to watch. Gee, these guys make a mess. That's okay though, they have the world's most effective central vacuuming system. This would be great in a house, unless of course you had pets. This is a gravure press. Unlike the offset presses, the gravure uses an etched roller to transfer the printing images directly to the board. Each roller rotates in a bath of ink, and a doctor blade skims off the excess. That leaves only ink trapped in fine etched pits in the roller. Also, unlike the offset presses, this one's fed from a continuous roll of paper. At the top of each tower is a heater that dries the ink before the next color is applied. But hot board doesn't print properly, so a set of refrigerator rollers cool the board before each new section. This press is capable of printing 8 colors, but often all 8 stages aren't colored ink. Depending on the package, the final stages can apply shiny coatings to the outside of the box and water-resistant coatings to the inside. The exact positioning of the printing done by each roller is sensed automatically by scanning a group of printed marks. This equipment adjusts the positioning of the print by adjusting the tension of rollers in the press. From here, the cartons go to the folder. Each one of these machines is custom configured for the box that it folds. This roller is applying glue to the underside of a flap on the box. Up and over. This is a pretty simple operation. These are bacon wrappers. Also a pretty simple operation. But this machine folds 70,000 of them an hour. Here's a slightly more complicated fold. It's a candy bar box. That big roller is applying glue at all the right spots. Okay, if a machine can do it, so can I. Well, that was my third try. This is a 6-pack and my personal favorite folding machine. A little glue, a fold, more glue. Here come 3 folds at once. Ready? The finished carton will be held rigid by the bottles that it contains, but can be folded flat for shipping. I wonder if I'll ever throw out an empty carton again without taking it apart first. The first step in preparing an item like this is to find some useless but interesting information on the subject. With this item, we hit the mother lode. A single whisker grows 15 1/1000ths of an inch per day. That's 5.5 inches a year and 27 feet during an average lifetime. The average male starts shaving when he's 15 and continues on to the average of 5.5 times a week until he dies at the average age of 75. That's 17,160 shaves by my math. The beard covers about 1/3 of a square foot and contains 15,500 hairs, or 130,000 hairs, depending on whose amazing facts you read. If the facial hair grown each day by American men were stretched end to end, it would reach to the moon and back every day. Rolled into a ball, that would weigh 25,000 pounds. Ancient Egyptians, they scraped themselves with sharpened oyster shells to shave, and Roman legionnaires ground off their whiskers with pumice. No wonder they were always in a bad mood. So there, pick your own intro, and if you don't like it, I'll give you your money back. Now, even though the electric shaver companies show animation of their product's interaction with your whiskers, they're still studying these machines with high-speed photography to see exactly what goes on. All electric shavers use a bunch of tiny blades moving rapidly underneath a thin piece of metal with holes in it. And as the whiskers poke through the holes, the rapidly moving blades cut them off. The design of the blades and the piece of metal with the holes is important, you see, because the blade, no matter how sharp it is, won't cut a whisker on its own. Moving those blades can be a simple proposition. This is the world's most simple motor. It's an electromagnet and a sprung piece of metal. When this is connected to 60-cycle alternating current, it oscillates back and forth rapidly. This unit's still found in some shavers, but it needs to be connected to a source of 60-cycle power to work. So shavers with this mechanism have a cord because they need alternating current from the wall plug to work. Shavers with this mechanism don't need a cord. It's a DC motor. I made it myself. The DC motor relies on the fact that an electromagnet will reverse its poles, north and south, when the current flow is reversed. Here are a couple permanent magnets and an electromagnet. With one polarity, they attract in one direction, and with the other polarity, they attract in the other direction. The DC motor automates this process. The electromagnets are mounted on a shaft and connected by contacts that brush against the contacts on the shaft. Everything's arranged so that when power is applied, the magnets on the shaft push away from the permanent magnets. The shaft starts to rotate. Now, the shaft would just rotate halfway around until the magnets were facing the poles they were attracted to, except for the arrangement of the brush contacts. Just when the magnets are happy, the contacts have reversed the current flow to the electromagnets around another half turn, by which time the contacts have reversed the current again. Now, if I did everything right when I built this, it should spin. Come on, baby. So there. The real DC motor uses more than one pair of rotating magnets, but the idea is the same. The DC motor in this shaver rotates 3 sets of blades via some gears. The one in this shaver uses a crank to create side-to-side motion. Well, there's the motor. What's all this other stuff? These are the cells that power the shaver. They're rechargeable. Good thing, too, because they're soldered in place. The electronics will take different forms in different shavers. All cordless rechargeable shavers use nickel-cadmium batteries. And they're the same as the ones you can buy for the kids' toys or your Walkman. Nickel-cadmium cells have to be recharged properly or they get destroyed. And the basic rule of thumb is to charge them at 1/10 the current that they can supply. There's a corollary to that. They take 10 times longer to charge than they last. As a matter of fact, they're perfect for use in a thing like a shaver. Interesting quirk of nickel-cadmium batteries is their memory. If you use them for 5 minutes and then recharge them, and repeat that cycle every day, they'll eventually develop a life of 5 minutes. So the best treatment for NiCads is to run them almost dead, then recharge them. The electronics in there takes care of all the proper charging rates. And some models can be used with a cord if the batteries are dead. In that case, the electronics have to be able to provide enough current to run the motor without cooking the NiCads. Science marches on, huh? During my research for this item, I switched from scraping myself with an oyster shell to shaving with one of these. They've come a long way since the last time I tried one. I wonder if the company's for sale. Just to save some of you the trouble of writing in, I thought I better show you this thing. This interface was hidden way over there during the first item, allowing my laptop computer to run 8 light bulbs. Now, microelectronics makes building things like this fairly easy. This great big chip is a universal asynchronous receiver transmitter, a UART. It takes the standard communication signals from the computer and decodes them into the 8-bit bytes you saw operating the light bulbs. The great big black lumps under there with the red tags on them are solid-state relays that allow the small currents these chips use to run big loads, 500 watts each in this case. Now, unfortunately, I can't send you the schematic for this. You see, with microelectronics, it's a lot easier to just build the thing than it is to bother to write out a circuit diagram first. So don't write in for the plans. There aren't any. Have a nice day.